bounding volumes. So previously in the flying chopper task, some of you created this code so that the chopper would stop moving left when its position in X was below a certain threshold, or stop moving right when the position in X was above a certain threshold. So what this code actually does is it creates a certain box around the chopper. So this +2 and -2 you had here was the sides or the length of that box, and this 10 and -10 were the boundaries of the hanger. So when this box intersects with the hanger, then you stop moving the chopper. So this is called an axis aligned bounding box because it's aligned with the axis. There is a very easy way to detect the intersections between axis aligned boxes. Visually we can see that these two boxes intersect because one of the corners of this red box is inside the green box. But implementation wise, it's actually much easier to detect the negative cases. So we can first check the horizontal axis. If this 4, which is the largest right coordinate of this red box, is below 3, which is the lowest left coordinate of this green box, or if 1, which is the left coordinate of the red box, is above 6, the right coordinate of the green box, then we know that there is no horizontal intersection and we return false. And we do a similar test for the vertical intersection. So if any of those conditions hold true, then we know that these two boxes do not intersect. They only intersect when they have both a horizontal intersection and a vertical intersection. And in that case, we return true. And again, code-wise, this is much simpler to implement than a positive intersection test. Generally speaking, we are testing if the maximum X of one box is below a minimum X of another box, or the minimum X of one box is above a maximum X of the other box. This is the horizontal intersection test, and the vertical one is the same with Y. And we can see that if we have a case where the maximum X of the red box is below a minimum X of the green box, then this red box has to be on the left from the green box. So there is no way they could intersect. Similarly, if the minimum X of the red box is larger than the maximum X of the green box, then the red box is to the right of the green box. And again, there is no way they could intersect. Of course, in 3D, you would also check for the Z coordinate. Now, if you have used engines like Unreal Engine, you might have seen these axis-aligned bounding boxes as one of the colliders. So those colliders are used for the same situation we had with the chopper before. The engines check if one collider intersects with another collider, and depending on the configuration, it could stop moving one of the objects with one of the colliders in order for them to not intersect. So axis-aligned bounding box is one option. You could also have a sphere. Testing an intersection with a sphere is quite an easy check. Or sometimes you use a capsule, so this capsule shape, which is a cylinder capped with two hemispheres. Or you might even have a convex hull collider. So this is a bit more trickier to test, but it's still easier to test than concave shapes. And some other interesting colliders are these 18 tops or 26 tops, which you can also find in Unreal Engine's colliders menu. Now what are these tops? They're called K-discrete oriented polytypes. They act just like axis-aligned bounding boxes, but they use extra axes. For example, down here we have this 8 top, and we can see how its shape changes from these different axes. So this is how an 8 top gets formed. So we have other thresholds along these diagonal axes. All we need to do to create a top is to have these axes represented with specific vectors, for example this vector 1, 1, and we just store basically the distance, the minimum distance of that box along that axis, and the maximum distance. To find these values, we have to take the dot product between each vertex and this axis vector. This would give us a projection of those vertices onto the axis, and we could just take the minimum and maximum values that we get. Detecting the intersection is just a generalization of the axis-aligned bounding box algorithm that we saw before. So we iterate over every dimension we have defined. We take the values along each of these dimensions, the values for one bounding box and another one, and we compare again if maximum of one box is lower than the minimum of another box, or if the minimum of one box is larger than the maximum of another box. If this is true for any of the axes, then we return false, and if it's not, then we return true. Note that these values don't actually need to specify the exact Euclidean distance. As long as they're on the same scale, this check will work. This means that when we have this vector 1, 1, we don't actually have to normalize it. Now there are different intersection testing algorithms between very different objects. The ones we covered in this video are just some of them. I recommend this book, Real-Time Collision Detection. It's a bit of an old book, but the math is still the same, so this is an extremely comprehensive overview of different bounding volumes, space partitioning, and the implementation. From this video, you should understand bounding volumes. They're often used as colliders in game and physics engines. They help simplify the intersection testing between different complex objects. So we don't have to test different complex triangle meshes, rather we bound them in some easier volumes called colliders, and we test the intersections between those. You learned about the axis-aligned bounding box. So this is one of the simplest bounding volumes, and we saw its intersection testing algorithm. And you also learned about the k-discrete-oriented polytypes, or TOPS, and these were a generalization of the axis-aligned bounding box. And we also saw their intersection testing algorithm, which was again a generalization of the axis-aligned bounding box intersection testing algorithm.